Deep beneath the massive peaks of the Swiss Alps, a sheer engineering anomaly exists. This is not simply a transportation corridor. It is a 57.1-kilometer-long automated industrial production line, permanently encased beneath 2,300 meters of solid, unyielding mountain rock. Welcome to the Gotthard Base Tunnel. At a staggering capital expenditure of $12 billion, this infrastructure stands as the deepest and longest railway tunnel in human history. However, to truly comprehend the magnitude of this megaproject, we must look far beyond the high-speed passenger trains. We must completely dissect the brutal physical limits of subterranean manufacturing and the extreme logistics required to conquer them. At a maximum overburden depth of 2.3 kilometers, the mountain mass is actively relentlessly attempting to crush any void hollowed out inside it. The vertical lithostatic pressure exerted on the tunnel crown reaches an extreme of 100 atmospheres. To visualize this structural load, imagine the sheer crushing force of a fully loaded freight train resting on a surface area the size of a standard dining table. This immense pressure is constantly uniformly bearing down on the newly exposed rock faces. Furthermore, the inherent geothermal gradient of the Earth's crust transforms this deep subterranean environment into an inescapable thermal furnace. Without artificial intervention, the ambient core temperature of the virgin rock stabilizes permanently between 46 and 50 degrees Celsius. In these extreme thermodynamic conditions, standard industrial operations become impossible. High-pressure hydraulic fluid loses its viscosity and degrades, sensitive electronic guidance sensors overheat and fail, and human operators would succumb to fatal heat stroke within a matter of hours. Therefore, before a single load-bearing concrete structure could be permanently installed, mechanical engineers had to engineer and deploy a massive continuous microclimate control grid. They constructed an industrial-scale ventilation and water cooling network, pumping an astonishing 3,000 liters of chilled mountain groundwater per second directly into the active excavation zones. Giant high-velocity ventilation ducts, spanning over 3 meters in diameter, forced millions of cubic meters of filtered air down the vertical access shaft. This aggressive thermal mitigation system successfully forced the ambient air temperature down from a lethal 50 degrees to a tightly regulated, manageable 28 degrees Celsius. This created a highly controlled artificial operational envelope, allowing both heavy tunneling machinery and human personnel to function continuously. However, thermodynamic control was only the first major physical barrier. The primary, overarching engineering nightmare of the Gotthard Base Tunnel was a severe geometric choke point. The final excavation profile for each of the twin, single-track tunnel tubes measures merely 9.43 to 9.58 meters in diameter. Within this extremely confined linear one-way static cylinder, a highly complex bi-directional logistics miracle had to be executed flawlessly. Consider the sheer, incomprehensible volume of the displaced geological mass. To bore a clear path through the base of the Alps, mining engineers had to excavate exactly 28.2 million metric tons of solid rock. To put that massive figure into a physical perspective, that is, the exact equivalent volume of 5 Great Pyramids of Giza. Now, imagine extracting that entire mass through a narrow, dark pipe, less than 10 meters wide, stretching for dozens of kilometers. Simultaneously, while this massive outward flow of crushed debris was continuously moving towards the portals, an equally massive inward flow of construction materials had to be maintained. A continuous, unbroken supply chain carrying 4 million precast concrete segments, thousands of tons of steel reinforcement, heavy machinery replacement parts, and rotational shifts of specialized workers had to flow inward without a single logistical collision. This bidirectional flow represents the ultimate industrial bottleneck. If the outward conveyor flow of excavated rock jams or stops for even 10 minutes, the massive boring machines at the front must immediately halt their advance. Conversely, if the inward train logistics delivering the concrete support segments are delayed by even a fraction of an hour, the freshly exposed, unsupported tunnel walls run the critical risk of catastrophic structural collapse due to unmitigated shifting rock stress. To prevent disaster, the project required a flawlessly synchronized, automated logistics engine, operating seamlessly 24 hours a day, 7 days a week, deep inside the high-pressure crust of the Earth. The margin for error was mathematically zero. The solution was to completely abandon traditional mining methodology. They transformed the deep underground caverns into a closed-loop, self-sustaining industrial supply chain. This was not a standard civil construction site. It was an ultra-precise automated factory where the raw input material was the very mountain itself, and the final output was a reinforced high-speed rail corridor. Every single moving part, from the multi-ton locomotives to the millimeter-precise robotic arms, had to operate within a strictly defined temporal matrix. This level of synchronization pushes the absolute boundaries of modern operational logistics, setting the stage for the deployment of the most massive subterranean machines ever forged by mankind. To execute this unprecedented subterranean logistics matrix, engineers deployed 4 distinct custom-built tunnel-boring machines, TBMs. However, referring to these mechanical structures merely as drills is a severe technical understatement. Each TBM, including the heavily modified gripper TBMs designated as Sissy and Heidi, operates as a comprehensive 400-meter-long mobile manufacturing plant weighing in excess of 3,000 metric tons. The core technology driving this excavation process is located at the absolute front, a massive cutter head measuring exactly 9.58 meters in diameter. This primary rotary component is equipped with approximately 60 specialized hardened steel alloy roller cutters. Driven by a complex array of high-voltage electric motors, the cutter head applies a staggering hydraulic thrust of up to 10,000 kilonewtons directly against the solid rock face, effectively pulverizing the ancient granite and gneiss bedrock through sheer mechanical compression and rotational torque. Once the rock is fractured, the critical closed-loop material extraction process initiates. The pulverized debris, technically referred to as muck, cannot accumulate at the cutting face. It is immediately scooped up by rotating buckets integrated into the cutter head and deposited onto a primary extraction belt. From there it is transferred to a high-capacity continuous conveyor system. This dynamic belt, which physically extends itself as the TBM advances deeper into the mountain, transports the excavated material back to the access portals at a continuous velocity of 4 meters per second. Furthermore, the 400-meter trailing gear of the TBM houses all the necessary auxiliary infrastructure required to sustain the operation. This includes massive electrical transformers converting high-voltage grid power down to operational frequencies, complex hydraulic pumping stations, and high-efficiency dust suppression systems utilizing atomized water sprays to mitigate the risk of explosive particulate concentrations in the confined space. Upon reaching the surface, the extracted material undergoes a rigorous industrial triage, revealing the true efficiency of the Gotthard logistics engine. The mountain's mass is not treated entirely as waste. Geological analysis determined that approximately 30% of the excavated gneiss and granite possessed the optimal structural density for heavy construction. Consequently, this high-quality rock is mechanically diverted into a massive, automated crushing and screening facility located directly at the portal site. The raw stone is meticulously processed, graded, and then combined with high-performance industrial cement. This recycled aggregate is utilized on-site to cast the millions of precast concrete segments required for the tunnel's structural lining. Following the casting process, these critical components are subjected to intensive thermal curing chambers, guaranteeing a structural compressive yield strength exceeding 100 megapascals MPa. Simultaneously, the inward supply chain must deliver these newly manufactured components back to the active excavation zone. A dedicated internal transportation network, utilizing narrow-gauge electric locomotives, operates continuously alongside the outward-flowing rock conveyor. These specialized supply trains travel the length of the tunnel and maneuver alongside the 400-meter trailing gear of the TBM itself, delivering the massive concrete segments exactly where they are needed without interrupting the forward drilling momentum. The culmination of this synchronized logistical loop occurs directly behind the active cutter head in the automated assembly sector. For every 1.5 meters the TBM physically advances into the mountain, the structural integrity of the newly exposed rock cavity must be secured immediately. This is achieved through the erector, an autonomous hydraulic robotic arm possessing extreme kinematic precision. The erector mechanically grips the precast concrete segments, each weighing an average of 10 metric tons, and hoists them into position against the tunnel crown and walls. The system systematically interlocks these massive geometric pieces to form a complete continuous load-bearing structural ring. The mechanical tolerance for assembling these heavy concrete structures is strictly mandated to remain under 2 millimeters. This extreme precision is absolutely critical. Any larger deviation would compromise the structural load distribution and risk a catastrophic failure under the extreme lithostatic pressure of the mountain above. The logistical timing is calculated down to the second. If the supply train arrives exactly 3 minutes late, the erector robotic arm remains idle. If the outward conveyor slows down by even 10%, the cutter head must reduce its rotational RPM to prevent a catastrophic backup of pulverized rock within the extraction chamber. This is a zero-sum mechanical ecosystem where maximum efficiency is the baseline requirement for operational survival. Every individual system, the rotational cutting, the continuous outward conveyance, the automated surface recycling, the inward rail transport, and the robotic ring assembly operates in absolute synchronization. This seamless industrial choreography allowed the TBMs to achieve a maximum theoretical advance rate of up to 40 meters per 24-hour cycle, slowly but relentlessly carving a permanent infrastructural artery through the dense heart of the European continent. While the automated tunnel boring machines relentlessly advance through standard geological formations, the true engineering nightmare materializes when the cutter head intersects highly unstable tectonic fault zones. In these specific sectors, the immediate mechanical installation of rigid precast concrete segments represents a fatal structural flaw. The extreme lithostatic pressure, generated by the 2,000-meter vertical rock column above, can spontaneously induce a severe phenomenon known within the industry as rock burst. This is a violent explosive release of stored kinetic energy directly from the newly exposed rock face, capable of instantly destroying standard support structures. To counteract this absolute physical limit, geotechnical engineers implemented a highly specialized yielding support matrix. Instead of rigidly attempting to resist the overwhelming compressive force of the mountain, the primary tunnel lining is mathematically designed to physically compress and deform. Heavy-duty deformable rock bolts, driven deep into the surrounding strata, are structurally combined with specialized sliding steel arches. These complex mechanical arches feature precisely engineered friction joints. When the mountain inevitably exerts its crushing pressure, these joints allow the steel profile to contract and slide upon itself, absorbing the immense kinetic energy. This sophisticated mechanism allows the surrounding rock mass to deform and stabilize in a highly controlled, measurable manner over several months, before the final, permanent, monolithic concrete lining is ultimately cast in place. The structural integrity of this permanent secondary lining dictates the operational survival of the entire $12 billion infrastructure. Therefore, every single batch of the 4 million precast concrete segments undergoes brutal, uncompromising load testing protocols before being cleared for subterranean transport. In dedicated surface laboratories, randomly selected sample segments are systematically placed into massive, computer-controlled hydraulic presses. Structural engineers conduct rigorous continuous stress tests, precisely measuring the dynamic elastic modulus and verifying the ultimate compressive strength of the composite material. Only when the material mathematically proves its absolute ability to withstand continuous mechanical forces significantly exceeding 100 megapascals without exhibiting microscopic stress fractures is it authorized to be loaded onto the inward-bound supply trains. This relentless data-driven quality control protocol ensures the 57-kilometer tube remains an impenetrable, structurally sound fortress against the crushing, perpetual weight of the European Alps. Once the primary structural shell is fully secured and validated, the final construction phase transitions entirely to the installation of the high-speed electromechanical rail infrastructure. Operating entirely within the completed strictly confined geometric cylinder, civil engineers completely abandoned the use of traditional crushed stone ballast and concrete sleeper tracks. The extreme aerodynamic forces, specifically the massive air pressure waves generated by two opposing trains passing each other at 250 km per hour within a tightly confined tube, would violently dislodge standard stone ballast, instantly transforming the rocks into lethal high-velocity projectiles capable of destroying the undercarriage of the train. The absolute technical solution to this aerodynamic hazard is the implementation of the continuous slab track system. Automated paving machinery, specifically modified and miniaturized for the tight 9-meter tunnel dimensions, continuously pours a monolithic, heavily reinforced concrete track bed directly onto the tunnel invert. The specialized steel rails are then mechanically fastened directly to this continuous concrete slab using heavy-duty, vibration-dampening polymer mounts. This highly specialized, continuous pouring process completely eliminates the risk of ballast displacement and achieves an absolutely rigid, permanent track geometry with construction tolerances restricted to a fraction of a single millimeter over the entire 57-kilometer span. The successful completion of the Gotthard Base Tunnel represents a massive, unprecedented paradigm shift in global macro-logistics and transportation engineering. By systematically driving a perfectly flat rail link directly through the impenetrable base of the Alps, maintaining a maximum track elevation of merely 550 meters above sea level, structural engineers have effectively neutralized the massive topographic barrier of the entire mountain range. This aerodynamic and geometric perfection allows massive, multimodal freight trains weighing up to 4,000 metric tons to traverse the tunnel corridor at sustained, uninterrupted speeds of 160 kilometers per hour, utilizing significantly less electrical traction power than required on older, steep mountain surface routes. Simultaneously, high-speed passenger transit reaches maximum operational velocities of 250 km per hour safely. This mechanical artery fundamentally restructures the entire European industrial supply chain, systematically shifting tens of millions of tons of heavy commercial freight from the congested surface highway network directly to this ultra-efficient, subterranean automated corridor. It stands as the ultimate undeniable testament to human engineering, a colossal, precision-crafted machine that continuously pumps economic life through the dense, solid rock heart of a continent. If you want to analyze the exact mechanical processes behind the world's most extreme industrial megaprojects, make sure to subscribe to the channel for more engineering breakdowns.